Hello students, here we are with section 2.2, polynomial functions of higher degree. And what we're going to focus on here is first using transformation sketch graphs of polynomial functions. We'll start with power functions and use some of the ideas from last chapter about how these can be moved around. The leading coefficient test, just like we saw that A in quadratics had a lot to do with if it was concave up or concave down, we're going to see that that leading coefficient, the coefficient on the highest degree term, is going to have a big impact on which way the function goes. Find and use zeros of polynomial functions as sketch names. Basically, I think you remember doing this. Find the zeros and then squiggle through the roots. Now, let's first of all talk about what a polynomial function is. We had some restrictions on polynomial functions. That is, all the powers on x had to be whole numbers. And so as a result, you end up with these nice continuous graphs with no sharp corners. So our polynomial functions here are going to be the ones that look like nice, smooth curves. These are not because of the discontinuous. This is discontinuous. And this one has a sharp corner. So basically, polynomial functions end up being smooth and continuous. Now, if all you have is just x raised to a power, that's just the first term in the general polynomial. It's called a power function. So these are power functions. Nice illustration of these, that if you've got an even power function, it's like the parabolas we talked about, but as we go up to x to the fourth and x to the sixth and so forth, it keeps having this y-axis symmetry. And they all end up being even in terms of their symmetry. P of negative x will equal P of x because x is an even power. Now, these power functions we use odd, you end up going to opposite infinities like this. You still cross the x-axis at 0, 0. But you lose that even symmetry and you create odd symmetry. P of negative x equals negative P of x for an odd degree power function. Here's a GeoGebra graph that employs something called a slider. This thing over here on the right is a slider, and I got it from this menu here where it says a equals 2. See that menu? Now I'm going to grab that slider and move it around, and you can see what happens to the function. Right now it's x to the first. That's a power function. We can slide over this way and it becomes x squared. There's the parabolas we looked at. Now we go to x cubed, we get our cubic, and then fourth degree, x to the fourth, ends up being even, fifth degree, sixth degree, seventh degree, and so forth. Notice these are all polynomial functions as well. If, though, I start going negative, first of all, n equals 0, that's still considered a polynomial function. That's a constant function. If I start backing up, though, we start getting bizarre things. See, these aren't polynomial functions anymore. We're going to study these later in the chapter, and they're called rational functions. Now, another thing you can do with sliders is you can control just how much. So if I change this to 0.1 instead of 1, now we can start seeing what happens, all the stuff in between. And we see it makes a more gradual progression. It occasionally flashes into fullness as we define over all the rules. Those are the polynomial functions. See? When you get n equaling a whole number, then you can use any real number in there for x. Something else, though, you're going to have fractional things. And that's what we see over here with one of our special functions, 0.5, that's the square root of x. And lots of things going on there. So y equals x squared. When you transform it with something like y equals x squared minus 5. Okay, so you'll have some homework on that. Now when we get back to polynomial functions again, that is not just power functions where it's x to the n, but polynomial functions. We have x to the n, x to the n minus 1, and so forth. You get all these extra terms. Those extra terms create these squiggles in the middle. And basically the leading coefficient now, the coefficient on the highest powered term, is going to tell you the direction. If n is odd, you can either have this sort of general upward trend, or if the leading coefficient's negative, then you'll have a general downward trend. The number of twists and turns we're going to see is going to be determined by this degree as well. So that means in a parabola when n equals 2, there's your turn, or the happy parabolas, we had one like that. As you can see in this cubic, and I assume this must be at least a cubic, it has 2 turns in it. And here, 1, 2, 3, 4. 4 turns. This is probably a 5th degree polynomial. Now, when n is even, you have both ends going toward the same infinity if a is positive. And if it's negative, they'll head down to the negative infinities. And we're going to classify these by the two things we just talked about. First of all, on this graph, n equals 3. That's odd. So it's going to head toward opposite infinities. Well, it's not an odd function. It's an odd degree polynomial, so it heads toward opposite infinities. And since a is less than 0, it's going to have this general downward trend. Here, on this one, n equals 4. That's even, so they're going to agree on the same infinities. And since a is greater than 0, the leading coefficient here, 1, is greater than 0. That means they're going to both head up to positive infinity. And on this one, we see n equals 5. That is, when I ask for the zeros of a function, that means the same thing as the end. Roots is equivalent to solutions. Later on in the chapter, we'll learn more sophisticated techniques of figuring out how to use the rational root theorem and so forth to get at those roots. Now, just a little terminology here. Multiplicity means when you come up with a root more than once. So in so that's this case. That's an example of k being even. This is multiplicity 2. So 3 is a root with multiplicity 2. We've referred to that in the past as a double root. And notice how you bounce off at a double root. Now, if you go a little higher, and let's say you have y equals 4th degree. And so to get that 4th degree, it actually comes down here, passes through the 0, and then passes through. So x equals 0 is a triple root. That's multiplicity 3. So it's odd multiplicity. So it'll actually pass through the axis. 2 is a root 2, but it doesn't really have any multiplicity. It's a single root, so you pass straight through. With roots with multiplicity that's odd, they'll tend to flatten out as they pass through. And you should reflect that in your graph. Now, here's our steps for sketching the graph of a polynomial function. We talked about how the leading coefficient tells you what the direction is, and also the degree of the polynomial. Find the real zeros of the polynomial. That's the roots. That's going to be where it crosses the x-axis. So you're going to be plotting those. Plot a few additional points. I suggest draw the graph then. Remember, it's got to be smooth and continuous. Smooth and continuous. That implies two ideas. Smooth, that means no sharp corners, like you have on an absolute value graph. Continuous means no holes, no gaps, no vertical asymptotes. And we're going to talk about those at the end of the chapters. Now, here's a few examples, and I've already punched one up here for us to look at. We're going to look at, let's put a star there on 45. And we can do more examples in class, but let's get through this one first. We're going to try and graph this and go through the whole 9 yards on this. So first of all, we see it's n equals 5. The degree, n equals 5. That's odd. And the leading coefficient is 1. That's greater than 0. So it's generally going to have a trend like that. And it could have up to 1, 2, 3, 4 turns in it. Up to 4 turns. So we've got the idea of the general trend we're going to make. Now we just need a few more points. So let's find the roots by setting y equal to 0. T to the 5th minus 6t cubed plus 9t. For now, all of these are going to be able to be done by factoring. So we can factor out a t. T to the 4th minus 6t squared plus 9. And then this is in quadratic form. So we can either let u equal t squared, or just, if you see right here, it's t squared times t squared will give you t to the 4th. 9 is 3 and 3. Minus 3 times minus 3, and then it'll add up to minus 6t squared. So now we can set each of these factors equal to 0. And so we get t equals 0. T squared equals 3, so t equals plus or minus the square root of 3. And again, t squared equals 3, so t equals plus or minus the square root of 3. Well, so we actually end up with 3 roots. 0, square root of 3, and negative square root of 3. But negative square root of 3 and square root of 3 showed up twice. So this is multiplicity of 2 for both these. So that means both these are double roots. And so when we graph this, when we graph this. When we graph this, we see that we got a root at 0 and a root at the square root of 3, that's about 1.7, and a root at negative square root of 3. But because they're double roots, we're going to passing through, and we say we want to start from below. I'm sorry, because they're double roots, they're going to bounce off. So we're going to start from below, work our way up like this, and bounce. No, so I bounced at the roots there, because those are double roots. Double roots visually means you're going to bounce off the axis. And 0 is a single root, so we pass through. Now I could clean this up with maybe one more point. Let's try 3, or let's see where 1 is going. 1 is an easy one to do. 1, P of 1, G of 1. For G of 1, we get 1 to the 5th minus 6 times 1 cubed plus 9 times 1. That ends up being 1 minus 6 plus 9 equals 4. So 1, I should have gone all the way up to 4 here. But you know, I wouldn't dock you on that. And negative 1 ends up going to negative 1 plus 6 minus 9. That goes down to negative 4. And I think we see a pattern here. Indeed, this is, let's get an eraser. This ends up being an odd function. This is odd. All the powers on the variables were odd. And if we look at the graph, sure enough, there's that 1 going to 4. And notice that wasn't the maximum. We'll use calculus to find out where the maximum is later on. Notice the bouncing off here at square root of 3 and negative square root of 3. And at the root of 0, it passes straight through. Finally, let's wrap up by actually doing one of these problems where we have the answers and we have to come up with a question. We have to come up with what the equation is. And I believe I picked problem number 71. So let's just, okay, here's 71. We've got the answers and we want to create the equation that goes with them. And it says n equals 4. Well, they happen to give us 4 roots. That's great. So we got from x, we got x equals 1, x equals negative 2, and x equals 1 plus or minus the square root of 3. Let's first just work on these two. X minus 1 equals 0, x plus 2 equals 0. If that was the whole question, we just multiply these two together, and we get x squared plus x minus 2 equals 0. That would be a second degree equation, a quadratic equation that has these two as roots. Now I got to deal with this too. Now when you get this plus or minus, I want to show you a little trick a student showed me. Actually isolate the plus or minus idea, and then square both sides. And it takes care of those two, so it's a lot cleaner way to deal with these. X squared minus 2x plus 1 equals, whether it's plus or minus 1 is going to get squared to be 1, square root of 3 squared is 3. So you get x squared minus 2x minus 2 equals 0. Now we end up multiplying these two together. X squared plus x minus 2 times x squared minus 2x minus 2 equal to 0. Because no, at least one of these has to be 0, so their product has to be 0. And now I'm going to use a little chart to multiply this all out here. X squared, x, negative 2. Maybe you've seen this chart before. X squared, negative 2x, negative 2. It's just a way to make sure you get everything multiplied. I usually do this when I have something bigger than a binomial, a FOIL, binomial times binomial. X to the 4th, x cubed minus 2x squared. X squared times negative 2x is negative 2x cubed, negative 2x squared, 4x, negative 2x squared, negative 2x, 4. I think you've noticed in the past here that the like terms are lined up along the diagonal here. So we get x to the 4th minus x cubed minus 6x squared plus 2x plus 4 for a constant term equals 0. And that should work. Flange out.